In, but I think that's okay. So welcome everyone. Great to see you all. A lot of familiar faces. Great to get this group started up again. Sorry it's been a while, but things are things often get crazy. But really excited to get this group going again and sort of I think in the sort of time that we are in, it's even more important to have these communities going to talk about issues with demographic estimation. So before we get going with the talk today, I just wanted to advertise as my role as associate editor at Demographic Research and also the co-editor of the Formal Relationships series. So I just wanted to flag to you all that this is a special collection that's ongoing in demographic research. If you're doing any formal or mathematical demography work, please submit to the special collection. It was started by Josh Goldstein and Jim Bopel. And then I've been co-editor with Josh for the past few years, and now Josh has stepped down to be more in an advisory role, and I'm very excited that Victor Garcia Guerrero is now co-editor with me. So just wanted to advertise if anyone's doing any cool formal demography work, please submit to the collection. So the talk today, really excited to have Hampton Gaddy with us today. So Hampton is a PhD student at the London School of Economics. Before he was at LSE, he did a bachelor and a master's at the University of Oxford. Hampton's work is sort of pretty far-reaching. A sort of central tenet is historical demography, particularly looking at issues in estimation around the 1918 influenza pandemic. But what I really love about Hampton's work is that he's just interested in questions about demographic measurement more generally, and a lot of his work really focuses on thinking really clearly and really hard about what we're trying to measure and how we can do a better job. So really excited to have him talk today about estimating excess mortality. He's happy to take clarifying questions during the talk, but we'll have a Q&A session at the end of his talk. So thanks very much, Hampton.
Thanks, Monica. I will try to do some clear thinking today. You can see my slides. Okay. Yeah. Right. So yeah, I'm a PhD student in the Department of Economic History at LSE, actually, which is a bit of an odd place to end up because my background is sort of training in the demography of contemporary populations, but I've increasingly ended up working on historical populations, especially the mortality of historical epidemics, and especially the 1918 flu pandemic, like Monica said. So today I'm going to be asking and show some work towards trying to answer a series of methodological questions that all have to do with how do we estimate the death tolls of mortality crises as accurately as possible. Whether that's a epidemic like the 1918 flu, or I'll touch a bit on conflicts, famines, natural disasters, and whether the crisis of interest is contemporary or historical. But I'll just start off by saying that, just so you're not surprised, a lot of the examples that I'll be giving, sort of case studies for the points I'm trying to argue, will be historical, because that is where sort of my work is right now for the most part, but also because I think that people who think of themselves as formal demographers or demographic methodologists, or like me, just someone who's quite interested in demographic methodology, I think we often don't recognize the extent to which historical data can be really interesting for the types of methods problems we're trying to work on. Because historical contexts often have a lot more data available than contemporary low-income countries, for example. And sort of there's more and more data every year with the mass digitization of historical data. But that data is really messy in interesting ways, sort of ways that are interesting to work on methodologically. in terms of the heterogeneity of the populations, and then also sort of issues around bias, completeness, and quality of the data themselves. So that's why I'm going to be talking a lot about historical context here, but I'm aware that most of the audience here works on contemporary contexts, and sort of I'm hoping that that won't put you off. Okay, so to get everyone's juices flowing, I will start off by thinking about talking a bit about what methods can we use to estimate the death tolls of mortality crises in general. So there are two methods that are commonly used that I think of as coming from the standard demographic toolkit. These are methods that I think most people trained in demography understand the intuitions of really well and could probably use themselves in a pinch if they needed to. So this is excess mortality estimation and intercensal cohort component estimation. Both of these do some type of observed minus expected comparison, where with excess mortality, it's sort of in a time series of mortality, you have a model of the expected number of deaths at any point in time, and then the excess deaths are the observed minus the expected. And then intercensal cohort component does a very similar thing where you take the age distributions from two consecutive censuses and look at observed minus expected in the change in the size of each individual cohort in the population, with some assumptions around expected model life tables and expected migration. So those are kind of the standard tools that I think make up easily 90 or so percent of the death toll estimation work that appears in quote unquote proper, like demography proper. But then there are other methods that kind of live more in other fields and then peek into demography every once in a while. So multiple systems estimation is a great example where it's commonly used in both conflict demography and population biology. And then there's kind of a world of ad hoc methods that will sometimes peek into contemporary demography, often peek into historical demography, but is often being done by researchers who don't sort of necessarily identify as a demographer. So sort of an example of an ad hoc method that is commonly used by demographers proper would be the sort of WHO and other people's work on the excess mortality of COVID in sub-Saharan Africa and other contexts with sort of limited vital registration, where often you do some sort of out-of-sample prediction approach based on non-demographic data in the context of interest, where you fit a model based on sort of the observed and where you have the data, and then predict what you think the unobserved deaths are in those contexts. So that's sort of ad hoc demography done by demographers, but then ad hoc demography not done by demographers, which is really common in historical settings, would be, for example, there's a medieval smallpox epidemic in Japan that's really important in sort of the context of smallpox studies globally, because it's supposed to have killed 1/3 of the population of Japan. And sort of is supposed to be a prime example of how deadly smallpox was in a medieval context. But that comes from no vital registration data whatsoever. It comes from extrapolations based on economic data that is available for Japan, right? So there's like this world of ad hoc methods that I'm trying to think about a little bit more here before pivoting to talk for the rest of the presentation about excess mortality estimation. And I start by thinking about all these different tools we have at our disposal, the tools we are familiar with, the tools we are less familiar with, because if we, I should swap to the next slide, yeah. If we did have perfect knowledge in sort of the context we're interested in, if we knew everything we could possibly want to know with no issues around data quality, the estimates of each method would be the same, right? For example, if we knew the exact relationship between socioeconomic and ecological covariates and COVID mortality in sub-Saharan Africa, we could predict that the death toll of COVID in sub-Saharan Africa perfectly without any uncertainty, right? If we knew everything, any method would be fine because we'd be able to sort of minimize all uncertainty in the application of that method. But since we don't have complete method in any particular context of interest, different approaches end up being more or less reliable in different contexts. And in any context, there's sort of some uncertainty about which approach should we use. And the questions I'm going to be asking today have to do with which contexts are which, right? Or rather, which approaches are appropriate in different contexts, and how do we know? And I'll just throwing some sort of papers up there because I think they're recommended reading for people who are interested in these types of questions, but also because they give you an idea of the type of literature that I'm kind of aspiring to contribute to here. The sort of first two papers are pre-COVID, the latter two papers are post-COVID and are sort of really interesting developments. I'll just focus on the latter two. We have a really interesting PDR paper by Nepomuceno and other Max Planck colleagues on the sensitivity analysis of excess mortality due to COVID. Jonas Scholle has some other work sort of that parallels this. And then a paper that I can't recommend enough to people is John Wakefield and Victoria Knutsen's excess mortality estimation, which is a paper that's in review, in press in the annual review of statistics right now, where they point out that in the context of excess mortality, which I'll spend a lot of time talking about today, people are doing all sorts of different things to estimate excess mortality. And it's not clear which approaches are sort of appropriate, more or less appropriate approaches in different contexts. So trying to contribute to this type of methodological inquiry, I'll be asking four specific questions today. So first, I'll be talking about a particular ad hoc literature asking, can we estimate death tolls by subtracting population estimates? In a few minutes, it'll be clear what I mean by that. The second and third question overall come as a pair because they both have to do. Hal, do you have a clarifying question right now? Yeah.
I do. I do. You've used several different words, and I'm not sure I could that I'm clear on the definitions of them. Death toll, mortality, excess mortality. Um, can you give one sentence definition of what those things are?
I think that will be. I see your point. I think that the yeah, no, it'll come up, but it's also worth clarifying now. Um, Death toll is well, part of the problem is that it's not because you could take a sort of like a medical definition or a counterfactual definition of a death toll, for example, right? And those end up looking like different things, and that is relevant to some of the questions
Its
I'm asking today. But
its units are numbers of people.
um, or proportion of population, yeah,
Okay, so those are two very different things.
yes. But what I have in mind will maybe come up through the presentation. But I would, for example, distinguish death tolls versus excess mortality, as excess mortality is the result of a particular calculation where the death, well, potentially the sort of counterfactual death toll is the estimand of what we have in mind, but not necessarily, depending on the type of what type of work we're trying to do. But hopefully things will come up and we can talk more throughout if it's unclear.
Okay,
So
okay. Carry on,
thanks.
carry on. Thank you.
So the second and third question overall come as a pair because they both have to do with excess mortality modeling, but also because they relate to one sort of overall question of what unit of analysis tends to yield the most accurate excess mortality estimates. So, and to Hal's point, that would be the excess mortality estimate that is closest to the true unobserved death toll based on whatever our definition of the death toll is, right? Whether that's medical or counterfactual, for example. And just to give you an idea of what I'm talking about here, so if you apply an excess mortality model to some national data set around an epidemic context, you'll get one national death toll estimate. But if you zoom into the state, county, province, local level and apply the same model at that level, get your point estimate there, and then sum those estimates back up to the national level, depending on the model, you may get a different national death toll estimate that's rather higher or lower because things don't aggregate perfectly for good reasons. And so the question here is which approach tends to yield more accurate excess mortality estimates? And sort of within that, I'll be first asking when does aggregating, so focusing on the national level in the first instance, for example, obscure the baseline level of mortality, which is something you need to estimate for your observed minus expected calculation. And then third overall, I'll be asking when does disaggregation, so when does zooming in the first instance, start to cause problems in terms of statistical power, in terms of the underlying population sizes of interest being too small to sort of meaningfully define excess mortality within. And then fourth and finally, overall, I'll be talking a bit about when does death registration incompleteness obscure the correlates of crisis mortality, however you're calculating that crisis mortality, that crisis death toll. And so, for example, here the question is, when do deficiencies in vital registration systems between social groups start to impair our ability to estimate the inequality between those groups in a mortality crisis setting, right? And before diving into these questions, I'll just say that the progress of my thinking with respect to these four different questions is in very different stages of development. So for the first question, the ad hoc question, this is the subject of a paper that came out last month in Demographic Research by myself and Maria Gargiulo. This is also the first chapter of my PhD thesis. The third question overall, the disaggregation question, is the second chapter of my thesis, and I sort of have a working version of this at the moment, but I'm not entirely happy with how I'm making the argument and what exactly I'm arguing. So I'm trying to workshop that with people right now, including you all. The second question overall, the aggregation question, I need to come up with some working solution to it in my PhD project, but it's probably going to end up being a much bigger project. And then the fourth question overall, it's quite early days. I have some interesting data I'm playing around with. I have some theory that motivates why I'm asking this question, but it's not clear what the paper will look like yet. So I'll start off by asking, can we estimate crisis death tolls by subtracting total population estimates? That is the title of this paper out in Demographic Research last month. By myself and Maria Gargiulo. Maria is a human rights and conflict demographer, and I'm often a historical demographer. And the reason we're asking this question is because in historical demography, my side of things, in conflict demography, Maria's side of things, there are a large number of papers out there that do use some type of ad hoc method to estimate a death toll through some type of subtraction exercise. So the simplest subtraction exercise would be a simple A minus B pre-crisis population estimate minus post-crisis population estimate. And to be clear, these are total population estimates, not age specific, for example, right? The simplest A minus B is what we sort of label here as method one. Method two introduces a bit more complexity and perhaps realism by introducing some intermittent growth rates, where you project forward from a pre-crisis estimate to the time of the crisis, project backwards, and take a discontinuity there that you take as your death toll estimate. And so on and so on. In total, we identify about 7 different stylized sort of types of model that all try to estimate a death toll through some type of extrapolation and measurement of a discontinuity, some pre and post-crisis population estimates, some model of intermittent population growth that contains a discontinuity, which is our death toll estimate. And in total, we call these 7 different models the growth rate discontinuity method. And just to motivate for you why we've spent time working on something that appears to be so crude, and that's because this type of subtraction exercise is really widespread in historical and conflict demography. So the simplest A minus B subtraction method is the source of the death toll estimate for the quote unquote deadliest war in human history, which is this civil war in 8th century China that's supposed to have killed more than half of the Chinese population, and therefore a pretty large proportion of the global population. It's also the source of the death toll for the quote unquote deadliest earthquake in human history, which is supposed to have happened in 16th century China. It's commonly used to estimate kind of a cumulative death toll for the atrocities in the Belgian Congo under Leopold I. And then this is the canonical method that's used to estimate the death toll of the Armenian genocide. Jakob Bijak and Sarah Lubman have a really helpful review chapter from the University of Southampton, have a really helpful review chapter where they point out that all of the sort of scholars and non-scholars who are arguing sometimes viciously about what the death toll of the Armenian genocide was are not actually doing anything methodologically complex. They are all using this sort of model of estimating things and simply arguing about how many Armenians were there before and after the genocide. And I can go out over like maybe a surprising number of interesting case studies like this, but just to give you a few more to motivate your thinking here for why we've written this paper. The sort of method 2 here, where you introduce intermittent growth rates, is the death toll estimation method used to estimate the death toll for the Trail of Tears, which is a very important episode of ethnic cleansing against Native Americans in US history, commonly applied to the Taiping Rebellion, a very influential civil war in 19th century China. I got into all of this because it's also commonly applied to estimate the 1918 flu death toll in important contexts like British India and Java. And then this is also sort of the often somewhat canonical estimation method for the Rwandan genocide. This type of GRDM work is where most of the available death toll estimates for the Rwandan genocide come from. And just to throw a few more out there, this particular model out of the 7 has produced kind of canonical death toll estimates for the Philippine-American War, the partition of South Asia, the Mau Mau Rebellion, which is Kenya's anti-colonial war of resistance, and also the North Korean famine of the 1990s. And so despite this method's crudeness, it's a method that is quite important to a lot of different academics and stakeholders. And so we try to take it seriously as a demographic method by first asking, how do the results of GRDM compare to the results of more standard demographic methods? This is the figure that summarizes our work towards that goal. Here we've identified 8 mortality crises where researchers first applied GRDM to estimate the death toll, and then later on researchers were able to use more detailed demographic data to apply more of a standard method like excess mortality modeling, multiple systems estimation, and a cohort component approach. And going from the top down, starting with the genocide in Timor-Leste in the 1970s, the GRDM death toll estimates there are the purple triangles. And this shows that the sort of before more rigorous demographic work was able to be done on that context, people were estimating death tolls anywhere between 10 and more than 50% of the pre-crisis population. But the sort of red dot with the error bars there is the estimate that comes out of the quite good multiple systems estimation work in that context, which shows that it's very likely that the true death toll is at the very low end of that very wide range of death toll estimates estimated with GRDM. So most of the GRDM death toll estimates available in that context are 2 to 3 to 4 to 5 times overestimates. Skipping down 2 lines, you have the opposite problem where GRDM massively underestimates Patrick Huveline's quite solid estimate from that context. And then for the rest of the plot, you have the problem where GRDM seems to massively overestimate. That's the case in Java in 1918, also Japan during the 1918 flu, the Bosnian genocide, and the Mau Mau Rebellion in Kenya. In British India in 1918, you have sort of a similar problem with Timor-Leste, where some of the estimates, GRDM estimates, overlap with some of the high-quality death toll estimates, sort of standard demographic estimates that we have confidence in. But some of the estimates are sort of significant underestimates or overestimates. It's only in the context of the second row here, which is the Irish potato famine, where the GRDM death toll estimate is decent, let's say, only about 20% out from Cormac O'Grada's canonical work on the topic. So this summary of this part of the paper raises the question, if you had a GRDM death toll estimate in isolation without any more standard, more detailed demographic work to compare it to, how much confidence would you have in that estimate in isolation, right? Given that the track record in the literature to date is that GRDM is kind of a method without an appropriate use case for the most part. where a single GRDM estimate can give you a lot of confidence that you have estimated the death toll well, right? So in another part of the paper, we do some simulation work that shows that this poor track record in the literature is not that surprising. So we systematically look at kind of everything that can go wrong when estimating GRDM death tolls. And it's quite easy for things to go wrong. Sort of very small amounts of error in the input parameters propagate to very large amounts of error in the death tolls of interest. So, for example, if you have a 1% change in census completeness from a 98% pre-crisis census to a 97% complete post-crisis census, then all else being equal, you're going to misestimate the death toll of interest by 1% of the total population size. Not 1% of the death toll, but 1% of the total population size, which might not be a huge error in a genocide context, but tends to be quite a large error if you're looking at an epidemic or a famine or a non-genocidal conflict. It's also similarly easy to misestimate what the intermittent growth rate is in context of interest, and you end up misestimating by a few percentage points of the total population. You also have this problem where the quote-unquote death tolls, these discontinuities that come out of GRDM, are not just influenced by the mortality impact of the crisis of interest. They're also sensitive to fertility and migration responses of the population of interest. And in this section of the paper, we take the case study of the 1918 flu in British India, where the pretty high quality excess mortality work that's also corrected for death registration incompleteness in that context suggests that the death toll of interest is about 17 to 19 million people, which is about 7% of the contemporary population of South Asia. But if instead of using sort of excess mortality estimates, estimation, if you use GRDM and you allow for just pretty plausible amounts of uncertainty on each of the parameters, you end up with a death toll anywhere between -1 million and 39 million people dying, which is an uncertainty interval that's, probably does contain the true value, but it's also an uncertainty interval that's so wide as to end up, I think, pretty practically meaningless. So to start to wrap up this part of the presentation, move on to the other questions. We think that GRDM is really interesting. We think it presents a problem for quite a lot of demographic and also I'll briefly say econometric work. I've already foreshadowed that this is a problem for existing demographic work because there are many crises, mostly historical crises, but sometimes more recent crises for which the only death toll estimates available come from GRDM point estimates at the very least. So I think one way forward would be to estimate uncertainty on GRDM like we do in the 1918 British India case, but sort of practically we think that you're going to end up with such wide uncertainty as for things to be meaningless. And then on the econometric side of things, that's not so much for this audience, but there's also sort of a parallel problem where we think that GRDM measurement error tends to be so large that it's not entirely credible that some political scientists have, for example, used GRDM to proxy the death toll, violent deaths during the partition of South Asia, for example, and then tried to partition blame to the presence of certain ethnic or political minority groups or certain ecological factors during partition for what sort of caused the violence. What we're afraid of here is that these estimates, the GRDM estimates in those contexts, are simply picking up the pre- and post-crisis characteristics of the population of interest that have to do, for example, with changes in state capacity before and after a partition, causing changes in census completeness in a way that might very well be associated with the presence of certain political or ethnic minority groups, but isn't associated with the true violence, right? So you end up with this issue of endogenous measurement error that's quite difficult to parse out in sort of the many econometric papers that do this type of thing. So our conclusions about GRDM overall are that if you have enough information about the demography of the population of interest to estimate the GRDM parameters well, you probably have enough information to use a more robust method. For example, if you're able to estimate the census completeness in a very difficult context like the ones we've been talking about well, you almost definitely have decent vital registration data that you can benchmark the census against, right? Whereas if you lack that data, qualitative information could very possibly be more reliable. So going forward, we say that past results and conclusions that have been drawn from GRDM should be revisited, and more time should be either, sort of depending on people's skill sets, spent developing new methods, for example, more robust ad hoc methods that can be applied to the context of interest, or we should spend more time collecting data that can be used for excess mortality estimation, for example. So that's the end of sort of the summary of mine and Maria's paper. And I leave you there saying, well, GRD is probably always less reliable than excess mortality estimation is, at least in a context where you can adjust for incompleteness of the vital statistics. But while that's almost certainly true, it kind of belies the point that excess mortality estimation itself is not a trivial thing to do, right? And there's a whole growing methods literature about this, which you may well be familiar with. But just to sort of go through some of the common problems, to sort of see what the literature I'm trying to contribute to here. So if you can take the observed number of deaths during a crisis context for granted, because you're not worried about death registration incompleteness during the crisis, then what usually goes wrong with excess mortality modeling is that you misestimate the expected number of deaths during your crisis in the absence of the crisis, right? I'm mostly going to be talking about excess mortality here in sort of a counterfactual setting, but that sort of means different things to different people, and not everyone thinks in a counterfactual approach. And we can talk about that if people would like. But when you're estimating the expected number of deaths, many things can go wrong, especially in a historical setting, where, for example, your pre-crisis of interest baseline might contain crises itself. So the classic example with the 1918 flu here is that in 1916 and 1917, Denmark experienced really severe measles and pertussis epidemics, which means that depending on your model of how you estimate the expected number of deaths, you can very easily overestimate the expected number of deaths in 1918, because in 1918 itself, there are no other epidemics besides the 1918 flu. And it's very easy then to overestimate the expected number of deaths and therefore underestimate the excess number of deaths by more than 50% in the Danish 1918 context. Then other things that can go wrong, or at least complicate things, are when you have all-cause data, but you have multiple crises co-occurring. For example, in Iran during the 1918 flu, you also have a really severe famine going on. You can also have a problem where you end up with negative excess mortality estimates, and people have different ways of dealing with that, but sort of we can agree that it's a problem that suggests that the expected number of deaths can be quite difficult to predict in any period. Then you can have issues of poor model fits, for example, where your mortality baseline has seasonality in it, but you don't account for that seasonality in your model of the expected number of deaths. And each of these problems already have best practice solutions of some kind in the literature. For example, when you have crises in your baseline period, one suggestion is to use temporally granular data to identify those crises, exclude them from the training data for your model of expected deaths, and refit that model. When crises co-occur, you can try to use different techniques to estimate the proportion of excess deaths due to each crisis. When excess mortality estimates are negative, depending on what your estimand is, John Wakefield and Victoria Knudsen suggest that you should ignore the negative components and at the very least recode them as zeros. And if you have a poor model fit, you can try out different model fits, or Ricardo Duerst and Jonas Scholle have a great new paper where they argue you can use empirical prediction intervals to try to account for some of your uncertainty in the model fit, or the appropriateness of the model fit. Now, my contribution in questions 2 and 3 here is twofold. First, I'll be arguing that when your baseline period contains crises, it's not always sufficient to just use temporally granular data. Sometimes you also need to use spatially granular data. And then for the third question, I'll be bringing up a new problem here that many people have thought about before, but haven't really codified their intuition of the problem or what a solution might be. I'll be pointing out that you can easily end up with population sizes that are too small to estimate excess mortality accurately in, especially in a historical setting. And the approach there is probably to merge units of analysis in some targeted way. And taking these 2 points together, so as I said at the beginning, I'm presenting them together because they both have to do with units of analysis, but also I'm presenting them together because taken together, they suggest kind of a general insight that I haven't seen anyone been making before, which is that excess mortality models can only estimate the underlying counterfactual of the expected number of deaths well at certain levels of disaggregation in your mortality data. This implies that there's, in any particular analysis, there's some optimal unit of analysis, spatial analysis, below which and above which excess mortality estimates will be biased. And then what that level is depends on a bunch of things that I'll start talking about now. So the first question is, when does spatial aggregation bias the expected number of deaths in a particular setting? So just to talk a little bit more about the existing problem of temporal heterogeneity and temporal disaggregation. So when you have an example like the measles, pertussis, flu epidemics in rapid succession, like in 1910s Denmark, the suggestion is to use temporally high frequency data to identify when the crises occur, then remove those crises from the training data and refit your model. And on the right here, I just have some example data to build intuition for this, why you need the temporally granular data. So here we have daily number of deaths in New York City around the 1918 flu. And on the right, you have the 4 waves of the pandemic, but on the left, you have a heat wave in the summer of 1917. And that heat wave isn't representative of what's happening in the 1918 to 20 crisis period, because there are no heat waves in that period. And so the argument is you identify that crisis, remove it from the data, refit. And you need temporally high frequency data to do that, because if you had monthly or certainly annual data in the New York City context, 1917 wouldn't stand out as an unusual year. You can only identify the crisis with sort of the daily or weekly data. And so without the temporally granular data, you have this sort of baseline crisis lurking in your analysis, biasing your sort of excess deaths of interest downwards. So my contribution is that there's, or at least my observation is that there's an equivalent problem and solution over spatial units of analysis. Because some baseline crises only occur in certain areas, they can only be identified using spatially disaggregated data. And depending on the context, if we don't use that spatially disaggregated data, we'll end up underestimating the excess mortality of interest. So to kind of empirically demonstrate this point, I've been playing around with an interesting data set that's just been published by some Danish researchers, coincidentally. This is a figure from a new American Journal of Epidemiology article where they think they've identified every single epidemic in Denmark over about a 100-year period from the 1810s to the 1910s. And to demonstrate my point about the need for spatial disaggregation, I've been focusing on this particular set of epidemics, which is scarlet fever epidemics, and asking how does our estimate of excess deaths at the time of these scarlet fever epidemics change if we do or do not account for the fact that just 2 years earlier, there's this series of cholera epidemics. So I've been checking alternately if you sort of leave those cholera epidemics lurking in your data, as I was just talking about, or if you use the spatially disaggregated data, as you need to in this context, to identify those epidemics, remove them, and refit the model. What's the change in our estimate of the scarlet fever deaths due to our change in the estimate of the baseline level? And it's about a 6% change. If you remove the cholera epidemics, you get a scarlet fever epidemic death toll that's 6% higher. Now, I'm not entirely thrilled with this as my example because 6% isn't a huge change, and also because in theory, you can have much more severe biases. So the extreme case here is if you have spatial units of analysis, sort of A through F here, that all have a pandemic of interest at the end of a time series on the right there. And in every temporal unit of analysis in your baseline, each spatial unit of analysis has a mortality crisis of an equal size. So that when you aggregate them together to, say, the overall national level, your baseline looks perfectly smooth because all of the crises are out of sync with each other. And so no matter how much temporal disaggregation you have at the national level, you'll never notice, never be able to detect that there is any crises lurking in your temporal baseline. So this is the most extreme case, and sort of they're in this sort of extreme, ridiculous, but sort of interesting case where the pre-pandemic crises are perfectly out of sync with each other, and then there's no crisis overlapping with the crisis of interest. You get this particular formula governing the underestimation you get. And, at least in theory, you could get 50 to 100% underestimation of the death toll of interest in this extreme setting. So that's kind of as far as I've gotten on this particular topic, so I'll move on to the next one, but hopefully it's clear that this sort of issue of a need for spatial aggregation, disaggregation is interesting, because if we don't account for it when we need to, we'll end up having death toll underestimation, and also that underestimation will be disproportionately worse in populations with more spatial heterogeneity in their baseline mortality, which would create problems in a regression setting, for example, whether that's a sort of a regression setting with a descriptive or a causal aim. So the solution here should be some amount of spatial disaggregation. But my sort of third line of thinking is that spatial disaggregation comes at a cost. So I don't necessarily need to say this for this audience, but you can think of excess mortality modeling as a battle between the signal and noise in your data. The signal of the crisis that you're trying to estimate the size of, and the amount of noise in your baseline data. Because when the baseline is not very noisy, it's quite easy to sort of predict with confidence what the expected number of deaths during your crisis period would be in the absence of that crisis. Whereas if the baseline is much noisier, you end up with a lot more uncertainty about what your expected number of deaths should be, and a lot more uncertainty in your excess mortality estimates, maybe an unhelpfully wide amount of uncertainty, sort of as we saw happens with GRDM usually. So yeah, noise. The reason I'm starting with this as your framing, or your signal versus noise framing, is because noise is a fundamental problem in small area estimation, as we can all appreciate. And so to start thinking about this and sort of formalizing an intuition of how small of an area is too small of an area for a particular excess mortality estimation exercise, we can simulate, for example, a population with a particular crude death rate at baseline that's hit by an epidemic that kills 0.1% of the population in a month, with your baseline counts drawn from a Poisson distribution, and check what's the distribution of excess mortality estimates depending on the population size. And this is sort of the result of that analysis, where if you have a population size of 1 million or 100,000 people, you're going to have a decent amount of confidence in excess mortality, because the possible range of excess mortality estimates, just due to the stochasticity of your non-crisis deaths, is quite small compared to the sort of death count that you're actually trying to estimate, the number of epidemic deaths. Whereas if you zoom down to only a population of 10,000 or 1,000 people, where you have 10 deaths and 1 death, respectively, sort of true deaths that you're trying to estimate, you end up with really wide, increasingly wide amounts of uncertainty in your excess mortality estimates, although the mean excess mortality estimate is not biased in this particular framing. But if you apply some sort of excess mortality model, as epidemiologists often do, where there's some implicit threshold, where you have a null hypothesis that there is no excess mortality, there is no crisis, and you don't reject that null hypothesis if the total number of deaths in a period isn't above a certain threshold. If you do this sort of threshold-based modeling, like circling regression that epidemiologists commonly use, you do end up with biased mean estimates quite easily, because in a very small population, if you just observe a death, you'll end up with very low, like just 1 death by itself, in sort of a time series of mostly zeros and ones. You're not going to have very high confidence that there was an epidemic at all, right? So yeah, sort of you have a problem with a huge amount of uncertainty in sort of most excess mortality settings, but if you introduce this sort of threshold, as many people do, you additionally end up with biased estimates overall, right? Usually downward biases. So building on this initial analysis, I try to think in general how small area is too small area, as a function of the size of the epidemic of interest, and also how concentrated it is in time. Because if you have an epidemic that's very widespread, you have a small death toll in any particular period. Also, I'm thinking about this as a function of the baseline level of mortality, the baseline dispersion of mortality, what your model of excess mortality is, or how you're sort of operationalizing it, whether there's a threshold or not, for example. And also then, so say you get these distributions of plausible excess mortality estimates out of your simulation. How small area is too small area depends on what standard you're applying to those resulting distributions. And I'll briefly show you some results that come from saying, well, in my particular context of interest, I want 95% of the simulated excess mortality estimates to be within plus or minus 10% of the true value specified in the simulation. And so our population size should be large enough to ensure that that happens. And applying that particular power rule, you get results that look like this. So on the x-axis is the proportion of simulated excess mortality estimates that are within plus or minus 10% of the true value. Population size is on the y-axis on a log scale. The facets along the top of the plot are the death toll as a proportion of the population in a single month. And the facets on the right are whether your baseline mortality is Poisson distributed or a negative binomial with quite a high overdispersion. And here, there's a lot going on here, and also the facet I'm not showing you is the changes in the baseline crude death rate, because that also matters quite a lot. But sort of to give you an idea for what I'm thinking about here, this suggests that, okay, in some populations, you can easily estimate excess mortality accurately in a population of 100 million people. But in some populations, you only need a population of 10,000 people, right? So in different contexts, sort of different amounts of spatial disaggregation will be appropriate depending on your sort of tolerance for uncertainty in your estimates, which will sort of vary case by case, right? And so in any particular analysis, we should probably be using prediction intervals, which is sort of not commonly done in a lot of excess mortality work, especially in epidemiology, to estimate the expected number of deaths in a particular context, and therefore sort of a prediction interval-based amount of uncertainty in our excess mortality estimate itself. And then in any comparative analysis, we should be considering the sensitivity of our results to small area measurement error and merge small units of analysis together in a targeted way to reduce overall uncertainty. And I'll just take 2 minutes on this last question, and then we have about 10 minutes for questions. Finally, I'm sort of in very early stages of thinking about, but I did want to sort of take to this formal demography group, sort of thinking about, in general terms, when does death registration incompleteness obscure the correlates of crisis mortality? So the theory that underlies this question is that in a mortality crisis, it's often socially marginalized groups that suffer the most. But even at baseline, the sort of official statistics often undercount the vital events of marginalized groups. And then in a crisis context itself, that undercount might intensify. And so if in a particular context of interest, we accept these first 2 points, and especially if we accept all 3 points, I think in any analysis of demographic inequality during a crisis context, we should be fundamentally worried about data incompleteness, right? And in my context of the 1918 flu, I've been thinking about this in the context of Alaska, where there's very high inequality between the indigenous and non-indigenous Alaskans. And both at baseline and during the 1918 flu itself, there's very significant evidence of under-registration for the indigenous Alaskans in the available death certificates, right? So there's a paper that's just come out, and a different paper that's just come out in American Journal of Epidemiology that tries to estimate the risk ratio for dying in the pandemic between indigenous and non-indigenous Alaskans. And they estimate an 8-fold difference. And this paper is great in all sorts of ways. It's sort of the best paper that's ever been done on indigenous mortality during the 1918 flu. But they have this crucial assumption that registration completeness is equal between the Alaska natives and Alaska non-natives. And if you take the sort of mortality data that they're using in this analysis, and even just look at the baseline period of 1915 to 17 before the pandemic. In red here, you have the non-Indigenous mortality benchmarked against the white populations of different US states at the time. And then in blue, you have the Alaska Native mortality, the MXs. And here, at the very least, we can observe probably a lot of things, but at the very least, it looks like there's this very odd pattern of death registration incompleteness, where over the age of 30, there seems to be massive under-registration compared to under the age of 30. Which is this very odd pattern that I don't have an explanation for, and I'm partly showing it because I would love if anyone had literally any ideas for what's happening here. It's not age misreporting alone, so there's something weird happening here. So that's as far as I've gotten on that point. But sort of the reason I'm giving sort of these four questions together, because it's a lot of things that I've been thinking about recently, about how, you know, we know that estimating death tolls is a difficult thing to do in a crisis context, and we can probably all accept, as, you know, even contemporary demographers, that this is probably true in the past for all sorts of data quality issues. But I think that there's also a lot of unacknowledged or under-acknowledged issues around what methods we can use when studying historical mortality crises. And we should probably be discussing these issues more and trying to build some community around trying to solve them. So that's the premise of this talk. So thank you.
Thanks, Gaddy. Sorry, everyone, I just managed to reach out now and Monica had to leave. So thanks so much for this presentation. And it's definitely becoming an ever-increasing issue with climate change and other crises. So it's just a formidable topic to have at the Formal Demography Working Group. So does anyone have any question, would like to reach out? So Robert, would you like to say it yourself, or do you want me to read? So Robert Chung is asking, for the 1918 NYC daily death data, how was the green line estimated?
Yeah, so the model of expected number of deaths.
Yep.
They have, so it's just sort of the standard epidemiologist approach of sort of a regression with some sine or cosine terms to account for seasonality. And then also they have, I think, weekly fixed effects thrown in there, right? Which is just one particular way of doing things. There's sort of a whole other question of what sort of results do you get if you make different choices in the construction of that model, right? And sort of, yeah, in that part, hopefully it makes some sense that my particular question is sort of the choice of what amount of spatial disaggregation you're working with, right?
Does anyone have additional comments, questions, or doubts they would like to clarify?
Hal, would you like to circle back to your question at the beginning of the presentation?
Yeah, it could also be if Hal wants to go back.
Actually, as you were showing different approaches and results in the different things, it became clear. I would suggest that it would be, from a general demographic point of view, it would be really useful to be specific about those terms. So a death toll in popular usage is often a number of individuals. How many people were killed in the attacks on 9/11? Those kinds of what's the death toll of traffic accidents on a major holiday weekend? Which is a different thing from a death toll as a percentage of a population, which is important in more relevant in some contexts. And similarly, mortality. Mortality can be numbers of deaths. It can be mortality rates. These different things. And I think it would be a useful thing to do to make sure that those usages are clear in people's heads, because they get at different aspects of these important crisis things. It's an amazing list of mortality disasters that you had at the beginning of your talk. Ugh.
No, that's a fair point. I keep that kind of vague though. Sorry, Jessica has just said in the chat. Yeah, of course. Feel free to email me. Thanks. Hal, so I keep it kind of vague because, especially when I'm trying to talk to different sort of constituencies of people who do this type of work. People often do a variety of things, right? And sort of I'm trying to speak to the question of both sort of death counts in an absolute term versus per capita, and sort of a death toll in somewhere in between a sort of something as an excess death or like a different sort of demographic accounting quantity, versus a popular conception of it, right? I think like these are all a sort of they're different concepts, but given that people do often use them interchangeably, I think it makes sense to think of working on them methodologically in sort of the intersection between these different definitions. Although, yeah, I take the point about clarity. Yeah.
I would argue that that the difference also has major implications for the way people think about policies related to these things. It's a standard thing that you see in discussions in the media, to jump back and forth between um, uh, sort of like uh, proportions of deaths caused by something, and then, well, there's more deaths caused by traffic accidents, and therefore your epidemic deaths are not worth worrying about. And um, the it can be a I don't want to say it's like a gambit that is sometimes used in arguments for people to obscure, to make a point about the importance or lack of importance of certain kinds of mortality events. Um, it's a sort of a underhanded argument trick, I think, and clarifying it is a valuable thing to do in that context.
No, that's fair. Thanks, all.
I agree with this last argument.
Yeah.
Something I cannot, something a mortal cannot say, but Hal Castle can say, so we can learn from it. Does anyone else have, okay, we have time for one short question or additional remark? I have a very, very quick comment, if I may, just based on your last slide. Hal mentioned this with this concepts, which I was also a bit confused. Sometimes you're talking about death toll. We always consider like absolute deaths, absolute cases of death when you say that as demographers, and sometimes you're talking it as interchangeably as mortality rates. So this is just a comment I have. But my question is that you're talking about disasters that many times are not, how can I say, they have a very disproportionate impact by age. But sometimes you have cases like with COVID, for example, where the disaster in this scenario is it happens in a way where the impact is very similar. So the pattern is very similar to what we already observed with in mortality overall. So cases, how would we proceed? I mean, how would you approach this? Because then how could you figure these impacts out? Or did you think about that at all? Like where we have disasters where you have a disproportionate impact by age, but others where it's just very similar to what the mortality pattern overall is already. So
Yeah. I think that, for example, if you have a pattern of impact that's very different from your baseline mortality, then you're going to be able to estimate the impact more precisely, right? Which sort of I was showing in the context of, all age, all cause death rates or death counts if we don't need to worry about population growth. But yeah, if you take an age-specific model, you're going to have the equivalent problem, right? Where 1918 deaths are a lot easier to estimate. Sorry, the death toll is easier to estimate in an age-specific model than COVID is in a certain sense because of the difference in the age distributions between the baseline and the unexpected deaths. Yeah. So thanks.
Okay.
Yeah, no, that's a good point. Yeah.
Thank you. Else? So I'd really like to thank your presence and willingness to present. I would just like to reinforce, together with Monica, that the group is back and we have like a very open agenda in the schedule. So we have some presentations already lined up, but we're very open throughout the year. So if you have anything you would like to present, just remembering you don't need to have like a finished work. The whole idea of this group was always to be very informal and be very open and to have this time where we have like-minded people that are sometimes nerdy about some things and just have work in progress and we'd like to discuss. So we're very open and we have this a fill out form or a link where we have on our website where you can just reach out, or you can reach out to me and Monica individually as well if you prefer, if you have something you would like to present or just discuss topic. It doesn't need to be anything completely rounded up. So the whole point here is to really receive feedback without feeling intimidated. So this is the whole idea. Yeah. So thank you so much, and I hope you can all be ready and present for the next meetup.